In this segment, we're going to dive into Seq2seq models, which stands for sequence to sequence. So the idea behind these models is they're going to allow us to flexibly handle a lot of different tasks that look like, well, mapping a sequence to a different sequence. So we saw this example from semantic parsing of we have these questions here and these lambda calculus representations here, and man, it's hard to do this with building a parser. And so what if we could just map directly from this text into this, this lambda representation? So it turns out you can even do syntactic parsing this way. This actually isn't the way that people build, the best syntactic parsers these days, but it's interesting that it kind of works at all. Where you take the sentence, "the dog ran," and we can say, all right, let's map it into this representation of a parse tree that just uses these kind of parentheses and labels in order to specify the tree structure. Now, there's some pretty big issues here. Like, what if we just change "the dog ran" and we put in "the dog ran" as input, and then it output "the horse walked" and a parse for that, right? So we're going to have to figure out how to address that. But this is a very flexible framework, and machine translation, summarization, dialogue, there's a whole bunch of problems that very naturally fit into this idea. And so it's one of the most sort of, pervasive ideas in NLP now is using Seq2seq models. All right, so what do these look like? So we're going to build off the ideas of RNNs that we started looking at for language modeling, where we encode a sequence into a fixed size vector. So we take the hidden state of our RNN after, quote unquote, reading an entire sentence. And then what we do is we have a second RNN over here, which we call our decoder, which is going to take this vector as input and produce a series of tokens, basically one per LSTM cell here, or RNN cell. So what's going on here is that at each time step in this decoder, we are generating the next word conditioned on both the previous word and also our hidden state so far. So at the first time step here, we have the hidden state which comes out of the encoder. So it should know about all the, the words in the movie was great. It should have a representation of the sentence. And then we feed in as input the start of sentence symbol, bracket S on the bottom here. And so this is an RNN cell, so it produces some kind of output representation, which we're going to call H bar. And then what we do is we just multiply H bar by a matrix W and apply a softmax to get a distribution over symbols in our vocabulary. So again, this vocabulary in machine translation, it might be the vocabulary of French words if you're translating into French. Or in our lambda calculus representation, it might be our kind of vocabulary of predicates and entities and predicates and lambda calculus symbols and things like that. So this gives us a probability distribution for this particular word conditioned on everything that's come before. And so we can generalize that to model an entire sentence. So here we have the probability of a whole output y conditioned on a whole input x is just the product over producing each individual output y conditioned on the ones that came before. So this decoder over here has separate parameters from the encoder, and one nice property of this decoders is that it's going to be able to learn to be a language model. So it's going to be able to look at what was already produced on the decoder side and say, okay, I think the next token is very likely to be this. And so it's going to be able to learn this kind of prior for what reasonable decoder output looks like for whatever task we're doing. All right, and so what I want to emphasize is that as we go to subsequent iterations here, we're going to need to, we had on the previous slide that we were conditioning on all of the previous y's as well. So we looked at every word that came before when generating, or every word that we've generated before when generating the next token. And so during inference in these models, we actually need to take the decoder at, let's say, time step 1 here, compute our argmax prediction, our kind of most likely word that we're predicting here, which is le. We're translating this into French. And then we feed that token into the next step of the RNN. So we fed in just this bracket S start symbol to start with, and then we predicted le. And we're actually going to take le and embed that token and feed that in at the next step. That's what this kind of fishhook thing represents. So there's no like fundamental reason we need to do this. We could just say, okay, you know, this RNN over on the right here is just not going to produce. It's not going to take any input at all. We're just going to let the hidden state kind of go along and figure everything out. This doesn't work very well though, and it doesn't let us model this sort of language modeling capability of what's a likely next word after le. Because it's only using the hidden state, which may be a sort of imperfect representation of what's going on here. So the tricky thing here from the standpoint of drawing these pictures is that we actually need to kind of evaluate the whole computation graph up until this point in order to figure out then what word we're predicting so that we can feed that in at the next time step. And then we kind of repeat this process. So after le, we predict film. After film, we predict été. And we keep going until the decoder generates what we call a stop symbol. Or maybe we have some different criterion, like we have a certain target number of words we know we want to generate, something like that. And so this is the basic template for how Seq2seq models work. They model this probability distribution for each word in the output conditioned on everything in the input and everything that's come before in the output as well. And using this RNN backbone, they're going to be able to feed information throughout this sentence. And so we're going to see that there's some pretty major shortcomings of trying to cook down our entire input into a single vector. But for right now, this is a flexible framework that's going to let us tackle a lot of these different problems. And we're going to see how to actually implement it and make it work. That's the end of this segment.